All right, good morning to the online and on-site audience. It's my great pleasure to have Mihaela here. She didn't allow me to do a long introduction. She said, "This is our cool friend Mihaela." That's literally what she told me. But I have to say that I will not tell you all your awards and everything, but as you all know, she's actually one of the most famous AI researchers in the world, also a board member of Alice, actually. And yeah, I knew all of that long before I met her. She's trying to cut me off. But you will see her talks are very inspiring. You have to check out actually her website. There's a item, Big Ideas, and I think that's very representative of Mihaela, because I think she's always in her thinking one step ahead, and I wish I had such a website. But now, because I'm not allowed to do a long intro, I hand over to her.
Thank you very much, Lena. And actually, I need to apologize to all of you. Yesterday, I saw an amazing talk in the AI conferences by Lena, and I decided to throw away all the slides I prepared for today's presentation and change it. So this is a talk inspired by Lena's presentation yesterday, but that also means that I hope it will flow, because it is really modulated by what she was saying. So hopefully it will be coherent. So my plan today is to talk about something that I call reality-centric AI, which is a little bit an idea that we are very much presenting not to people like you who are already working on reality-centric AI. By your simple presence being here, you are working on this topic. But many people in the machine learning community to which I appertain and many of you appertain are not working in what I call reality-centric AI. So I want to talk a little bit about that to make you hopefully feel good and join the cause. Not because you are not convinced, but because I want to get you on board to sell this topic to the bigger world of AI. And then I really hope to have a little bit time at the end to tell you what would be the role of academia in the era of large language models. How can we engage with them, and why we should be excited about them beyond just training large language models and fine-tuning large language models, which probably we can't do no matter how much computer power we have. You can hear me? Hopefully, okay. Okay, so we have seen tremendous advances in AI over the past couple of years, definitely with generative AI, large language models, but also in robotics. And yet, despite these tremendous advances, we have not seen fundamental change in healthcare systems. And I'm talking here about two countries I know well, United States, where I lived 18 years, and the UK, where I lived in the last couple of years. In the United States, healthcare systems are both inefficient and, to some extent, very ad hoc. In the UK, they are super stressed, and they are really not able to deal with the patient population to treat them in a timely fashion. So AI, despite its enormous potential, didn't do much to these important healthcare systems. But this is true in other settings. Whether it's traffic, I used to live in Los Angeles, where I was stuck in traffic for hours on end, despite the fact that I worked on AI for transportation, and other ideas in climate change, and why not in education? So I often say this half-jokingly, if a Roman schoolmaster would enter today this classroom, they would understand what's happening here. Not that much has changed despite AI in 2,000 years. And what I'm trying to say here is not that AI cannot transform these domains. What I'm trying to say is that the world of AI and machine learning needs to think differently about AI itself if it is to make these true transformations in the world for the better. And in our lab, we have worked over the past 20 years on many applications. It is only in the last 10 that we have focused a lot on medicine and education. But prior to it, all the way back to 20 plus years ago, we worked in communication systems, energy, economics, finance. And we always were problem first. So I work on AI, inclusively hot topics such as multi-agent reinforcement learning for more than 20 years, but in a problem-centric way. rather than methods first. We don't know what to do with it later. So I know I'm preaching to the choir, but partially because you are doing reality-centric AI, I hope you become advocates to your community about that. So what I'm saying here is that a fundamental new paradigm is needed for AI to address these complexities of the real world. And for that, I have written a manifesto, which I call Reality-Centric AI, where I outline the challenges on doing this reality-centric AI. And also I highlight multi-pillar agenda, 7 different pillars of what I think needs to happen in AI in order to see this change. I really hope you will look at this manifesto and you will write to me if you have ideas about how to improve it, or if you like it, or even better, if you don't like it and why. I'd really appreciate your feedback. So what is reality-centric AI? I will not tell you a lot about it. I'll let you read the manifesto, but in a nutshell, is reality-centric AI is the one that tries to solve real-world problems, starts with the problems, and operates effectively and accountably given the complexities of the real world. And it is an AI that aims at human empowerment rather than human replacement. And this does require a different way of thinking for the community of machine learning that happens in the main top conferences. And it's a community to which I appertain, but where a lot of non-reality-centric AI is happening. One of the important aspects of reality-centric AI is the fact that we need to deal with real-world data. And this was very motivated yesterday by similar ideas and similar thoughts in Lena's talk. So this is why a lot of the talk today will be about the second pillar of the reality-centric AI, which aims at dealing with real-world data in order to build powerful AI. What type of real-world data? Messy data, unfair data, complex data, erroneous data, unfair data, maybe at times no data. Could you do something if you have no data? Costly data, evolving data. So these are very important topics, and we have also worked on this area for quite a large number of years, and we increasingly are working on it as the most important problem in AI, or one of the most important problems in AI. And what I want to talk to you about today is 2 areas. One is the data-centric AI, the other one is the area of synthetic data. And then I'll move to the topic of large language models. Since I don't have a lot of time today, I want to point out that we have given at NeoRIPS a tutorial together with my brilliant PhD student, Nabil Sidat, and one of our close discussants, not necessarily a collaborator, but somebody with whom we share this ethos, Isabelle Guion from Google. We gave a tutorial about this topic, more focused on the data-centric AI at NeoRIPS, and this is available online for you to take a look. So I'll talk about a few things, but if you want to hear more, you can see it online. So what do I talk about when I talk about data-centric AI? We know that a lot of the machine learning community is focused on what we call model-centric AI, building better models, better architectures, better loss functions, better optimizers. That's the world of AI today, largely. But I feel that that's already much less exciting and to some extent much, much easier, partially because of the wealth of work that has happened in the last 20 years. What's much more overlooked and much more impactful, in my opinion, is the data-centric view, where the focus is on the data. How do we acquire data? What data to acquire? How to clean data? How to audit data? How to generate data? How to unify and harmonize data sets? And the model is, if you like, kind of taking second place. So how do we think about data-centric AI as encompassing models and tools to systematically characterize, evaluate, and generate the underlying data used to train and evaluate models. So I want to highlight first a paper which is not a method paper. It's a paper where we talk about all the different ideas that would be needed to build the pipelines for data-centric AI. We call this work DC-check, and again, I hope that you will engage with this framework of thinking. This is very much, again, Nabil's brainchild, and you can find this paper online, and what it does is really trying to identify across all the different stages of the design of a machine learning pipeline the role of data. From how to acquire and deal with the quality of the data, to how to train data, to train machine learning models using data, to how to test them accurately using data, and then how to deploy them and keep them in deployment. So what do I really have in mind here? So at the data stage, we have a variety of, let's say, methods that exist at times. At other times, we need more methods. So for instance, proactive data set selection and curation, pre-processing, data quality evaluation, and synthetic data. I'll talk quite a lot about synthetic data later. Then at training time, we still are in this stuck paradigm with I take a data set and I keep a hold-out data set and I'm going to maybe validate or test on it. But this is very wrong, and many of you know it, and I'll talk a little bit about that later. So we clearly need new ways to train models and evaluate models and validate models. And just to mention one of the many things that I think are very important is how can we really do better evaluation and training for different subgroups of interest, and if these subgroups of interest may be changing or are very unrepresented in the data, how to deal with this issue, such that we don't declare as a winner a model that's actually absolutely useless and may have fantastic accuracy, but may be useless in the real world. Again, a topic that Lena also discussed yesterday. Then at testing time, we want all sorts of stress test scenarios to be able to really maybe even test these models on data that we have not yet seen, but we anticipate that may be seen at deployment time. Either we may train a machine learning model in Heidelberg, but we know it will also be deployed in Cambridge, where a different type of population exists. How do you plan for that type of model testing? And more generally, evaluation beyond just looking at the average population. And then at deployment time, we know that there will be shifts, there will be drifts, there will be potentially need for continual learning and continual adaptation of the model. All of these different stages represent exciting areas where some work at times has happened, but a lot more needs to happen. It's a lot more understudy and a lot more impactful area than building yet the next diffusion model. And I'll go back on that rant in a little bit, while admitting that we are using and we are building diffusion models as well. But just to give you an example of what I find even more exciting than building the next model. One area out of this entire pipeline, that is very important is data characterization. And there is really an excitement to look at how to curate and audit data sets. And usually this is hard and time consuming and nobody wants to deal with it. But it's an enormous opportunity for machine learning. So not all data is equal, and often we would like to assign a score to individual samples in the data set. And we would like to do that across different types of modalities. We in our lab work much less on imaging data, much more on tabular and time series data, but I think that this problem is needed across all data sets. And actually multimodality may be a very important way to look at these problems. So, for instance, which samples are what we call learnable, which one are important, which are ambiguous, which are hard, which one are mislabeled. And just to show one of the things that we have done that's multimodal, most of our work focuses on tabular, but this work, which is called Data IQ, again by Nabil, is multimodal. We look at both imaging as well as tabular data. The focus was really to characterize heterogeneous subgroups and divide them into easy, ambiguous, and hard. why do we want to do this type of data characterization? And we look here not at epistemic uncertainty, so we are not looking at model uncertainty, but rather at aleatoric uncertainty, as well as hardness in the data, and try to characterize different types of data samples, either to be able to inspect them, to augment them, or even to remove them, depending on the diagnosis that follows. So Data IQ is one such tool. But what I want to highlight here is not just one paper. In our lab, increasingly, I'm trying to convince my students that in order to do reality-centric AI, we cannot just have our methods. If it is to really energize the community, we need to build entire ecosystems. So data gnosis is not a paper, but it is a resource that we have built together with Nabil and an engineer in our lab, Rob Davis, where we have a unified interface and API where we brought a lot of state-of-the-art methods, not only from our lab, but from other labs, and I hope from many of your labs. We are trying to bring more and more of these data characterization methods together. It has an easily extendable plugin style interface. And you can download it from our website. It is open source. You can play with it. You can compare your methods with it. And we hope that you will join forces with us to expand it. So again, open source, let's say, grassroots effort to try to build more data-centric AI. And again, here is the QR code, which contains some tutorials on how you can use it easily in your own work. And some of the work, again, is imaging. Some of it is tabular data. And again, if you want to hear more about data-centric AI, I'm not talking too much about it today, but I'm very excited about it. And we do quite a lot of work in the lab with a few students, especially Nabil. But you can see our tutorial to find out more about the work. What I will talk a lot about is an area that I really started, which is this area of synthetic data. So around 8 years ago, nowadays a lot of people talk about synthetic data, but at the time, nobody wanted to even hear me when I introduced the idea of using synthetic data as a way to really share data with colleagues in scenarios such as healthcare where data cannot be shared. So I want to tell you a little bit about the beginning of this agenda 8 years ago, which was motivated by sharing data and privacy preservation. But I want to move then very fast to the current time to tell you why I'm excited about synthetic data as being better than real data. So when I started, it was a second-rate copy, was really something that we were trying to replace real data with privacy preservation, but now we are wanting to really use it as a way of improving and enriching real-world data. So I'll talk briefly about synthetic data, then why I'm so excited about synthetic data as improvement of real data, and then a few words about trusting synthetic data, because of course it's easy to create and generate something, but God knows whether it's any good. So why synthetic data? So early on, I was very frustrated as I started to work in healthcare that I could never either access data of my collaborators or of my clinical collaborators, neither I could share my data that I got from my clinical collaborators with other AI collaborators. And of course, this makes sense because this is healthcare data. This is not cats and dogs and ImageNet, which we can easily put in the internet. Yet we know that ImageNet has led to tremendous advances in AI. So I was very inspired by ImageNet to try to see, can we really, by using synthetic data, can create a resource for medicine. And the alternative was, at the time, and still is, de-identified or anonymized data, but that has a lot of issues because often we don't de-anonymize enough, thereby being able to re-identify data, or we are de-identifying data so aggressively that the data is useless. So synthetic data is an alternative, and I think a powerful one, and is a machine learning problem in itself, because you need to generate synthetic data on the basis of real data. So how can then synthetic data help? is because we take real data, we generate then through generative models synthetic data, which we then need to thoroughly evaluate to make sure that we generate useful synthetic data for the task at hand. And then we can give this data to researchers for whatever purpose they need it. And hopefully these models that are generated on the basis of this synthetic data can be then given to the original data owners, hopefully clinicians, hospital patients. And this is kind of the manifesto that we wrote a few years back. It would be wonderful to have kind of an ecosystem where researchers can put these data sets, then synthetic data can be generated, which can then be given to researchers for competitions, for running machine learning, for benchmarking methods. Let's be honest, in the machine learning community, especially in the tabular data set, we just have Mimic and maybe another data set from Amsterdam. These are just two data sets and everybody is just working on these two data sets. And this is kind of not empowering for the community. In imaging, I think the situation is a lot better, so we are more fortunate, but still, we don't have many data sets. Let me say that the excitement I have is less nowadays on creating yet another generative models. Around 8 years ago, I was very interested in building generative models, from building the first time series generation method, which was called TimeGun, to many other generation models. We still work quite a lot on building deep generative models, but to me that's not the exciting part. The machine learning community, which is not very reality-centric, loves to find a new toy. In the past was GANs, more recently is diffusion models. And we ourselves worked on all these different topics highlighted here and built new methods. And yes, we are working on diffusion models as we speak. And yes, indeed, at iClear, we have 2 papers on diffusion models that are very cool in terms of methods. For instance, for time series diffusion and for error propagation. But the point is not, to me, the fact that we can do yet another cool toy. What I'm a lot more excited than the next diffusion model is about how synthetic data could be truly empowering for the world. And in 2 tutorials that we gave, the initial tutorial which I gave with my former student Ahmed Allah, who is now professor in Berkeley, we focused more on generative models and synthetic data for privacy preservation. The tutorial is still online and you can watch it, but we gave another tutorial last year at AAAI on innovative uses of synthetic data. And that's what I want to tell you a few words about, because that relates also to what Lena was talking yesterday. Before I do so, I want to get you again enthusiastic about something that I think it's even more useful than a method or a way of thinking. We built something that's maybe not so glamorous, but I think it's very, very useful. And I was delighted to hear that not only academics, but also Google and Amazon are using this a lot, which is an open source resource that we have built for synthetic data generation. For a variety of use cases as well as modalities. It is quite heavily built on tabular data because that's an area that we know a lot. It's much less good on imaging. So this is also a call to you. If you are interested in image generation, please contribute your best methods as well as your benchmarks to SynCity. So SynCity is an open source package aimed at really trying to create for researchers very easy to use prototyping paradigm with lots of benchmarks such that you can do research fast and reproducible. And it's also useful for researchers, inclusively for the Googles and Amazons. So if you are a researcher and you don't want to empower other researchers, but you want maybe a cool job in industry, let me tell you, this was a very useful resource for some of my students to highlight their algorithms and then get hired. So help us get into SynCity your methods. And quite a lot of the methods that I'll discuss today are in SynCity. So why I'm so excited about it is because I believe that with synthetic data, we can not only overcome the use of and transfer of data, but also we can augment real data. So this is better. That's the reason I call it powerful creation, not second-rate copy. And we can do a lot. So not only privacy preservation, but also simulation, adaptation, augmentation, prompting, and fairness. And I'll briefly tell you about this. So I'm going to start unusually with simulation, because that's what Lena talked yesterday. So one of the most interesting problems that I think we have in AI is that often we have an amazing method. It does really well at training time, but then we use it in the real world and it fails. And here is an example from Google, but I don't want to pick only on Google. I think this is true for all of us. Often it's happening that you have a fantastic method, it really works in the test set, but then you take it to another domain and it just simply doesn't work. And this is very important, and it is important to better evaluate our methods, because if we only test them on holdout data sets or data sets that we have locally, and we don't think about where are the uses of this data, of these machine learning models, we will produce methods that may have fantastic performance, but useless in the real world, because the real world is very different than the data you tested on. And these differences could be very diverse. It could be that the data is more noisy in your test environment. It has shifts, it has drifts, it has all sorts of imperfections. It may have more anomalies, it may have harder data. So you need to really take that into consideration. So shifts and drifts are the one that the community is more focused on, but the reality is that there are many other issues as well, not only shifts and drifts. So what I'm really advocating for, and I know I'm preaching to the choir here, is that reality-centric requires better model testing. So in a similar way, like in the aviation industry, they are doing everything they can to test subcomponents as well as the entire product. In a similar way, I think in the AI community, we need to test better subcomponents as well as the entire machine learning ecosystem before really giving them to clinicians or healthcare systems. We really need to have a better ethos in what we build. And I'm saying here, our group very much included. So one thing that I want to show to you, which is a recent begin from our lab, was to really use synthetic data to better do validation and testing of machine learning models. And what I'm talking about here is granular evaluation on different types of subgroups as well as distributional shifts. So often in your data set, you may have only very few people that have the condition of interest, or the very few people that may be of a certain ethnic group or gender. So you see here, for instance, that we have very few black women, for instance, or very few black elderly people in our data set. So this could be lack of representativeness. It could also be that it's exactly these patients that have a different outcome than the general population. Also, we often don't consider what will happen over time. So we know, for instance, in COVID that the population has changed, and yet we don't test for that. So in a paper that appeared last year at NeoRIPS, we started to look at how can we really improve model evaluation using synthetic data. And we call this paper free S testing, and the free S's are synthetic data for subgroup and shift testing. And what we do is not something amazing in terms of ML, but I think an important step forward for the machine learning community in terms of testing. So what we do is, in order to do this type of granular evaluation, we are training a conditional generative model on the real test set. And then we are generating conditionally very different types of subgroups with different types of shifts and drifts. And you may ask, where does this knowledge come from? This knowledge could come from just prior knowledge that you may have about the testing side, or about things that you may anticipate are happening. They could even come from a large language model. At this time, we didn't do that, but they could. So then what we are going to do is we are going to evaluate the machine learning models not only on the test data set, holdout data set that we have, but also on the shifts and drifts of this data through synthetic data. So through this conditional generation, we can emulate all these tests and select models that are not only doing well on the holdout real data, but also across all these different types of real-world scenarios that one may encounter at deployment time. Why this is important? Let's take an example here, and you see quite a few data sets from COVID to other data sets, where we show that if you just have a holdout data set, you may declare certain models to be best, but the reality is that these models are doing very poorly on subgroups of interest, or if the data will change somewhat, they suddenly are going to be very brittle. So just testing based on holdout data set, which is very much a golden standard, is not enough. On the other hand, if you can put this augmentation through synthetic data, you are able to select much more robust models for all these scenarios. And even better is, of course, if you do both of them together, both real and synthetic together. So again, I don't think that this is a complete fix, but this is a begin of trying to envision how can we use synthetic data to augment real data to better stress test our models. Can we do better? I'm sure we can do better. One of the many ideas that we can do better is through multimodality, where different modalities may shift, drift, may be very different in terms of the representation of the population. So I hope we can join forces together on that. Another area that we are interested in is fairness. And you all know that real data is often quite biased, and these biases will propagate to the downstream task. So another early use from our lab of synthetic data was to no longer use unfair data to build models, but rather use synthetic data to turn unfair data into fair synthetic data to train models on before giving them to the real world. How to do that? In a paper called Decaf, we use causality, and we make a very big assumption, which may not be true in practice in many settings, may be true in some cases, but not always, that we do have a true causal graph. And if we have this true causal graph, then we can use it to create from unfair data fair data. So we use this causal perspective to create different types of fairness notions and then kind of create fair data for the downstream task. So why we like causality? Because if we indeed would know the causal graph, we can eliminate all sorts of dependencies, thereby being able to deal with numerous notions of fairness, especially group fairness. So demographic parity, conditional fairness, etc. are all, let's say, can be instantiations that could be using this underlying graph and providing fairness. So somebody could say, I want this notion of fairness being instantiated, and then use the causal graph to eliminate the edges that are going to provide this type of fairness. One is to be very careful, though, because at times you may eliminate certain edges and you may say, okay, that my data is fair, but the reality is that through the back door, you still have a lot of unfairness. So you need to be really careful what you are doing, because just masking sensitive attributes doesn't mean that you don't have indirect discrimination. So this is where having the causal graph is a useful thing. And what we do is we learn here, we were still in the good old times of GANs, so we embedded such a causal model into a GAN. You can embed such a causal model into a diffusion model, which is nowadays popular, and do similar things. So what we do is we do generation that's aware of this causal graph, such that you can sever all the edges that are leading to different types of bias. So you can say, if I don't want to have this type of bias, at generation time you will sever these links when you do the generation. And what we do is step-by-step generation, so conditional generation. And then at inference time, at runtime, we are synthesizing topologically the variables using this causal graph, starting from the root all the way to the edges of the causal graph. And you can do it according to different notions of fairness. Is this enough? Clearly not. I think one could do a lot better than decaf, and especially the fact that we use a causal graph, I don't think it's so ideal. Can we do better? Can we do better in multimodality, etc.? Augmentation is another big issue for us. In imaging, you have been tremendously successful at doing augmentation, and we envy you. But in imaging, you are somewhat fortunate, I would say, because it is clear how to do augmentation. By shifting images, by rotating images, we know that we can augment the data sets. And such augmentation has been tremendously useful for the imaging community. So we were very much inspired by it, and we tried to say, well, can we do the same thing for tabular data? But for tabular data, this is tricky because we don't have such inductive biases. We really don't know how to augment. What type of changes we should make that still contain the inner consistency of the data, and we still have meaningful tabular data. So one idea is, again, to use graphs. This time, these graphs are not known in advance, but they are learned together with the data. So in this paper called Goggle, we are learning jointly tabular data and knowledge graphs, if you like. If we know them from experts, for instance, clinical experts, then you can inject that prior knowledge. If you don't, you are learning it directly from data. So what we do in Goggle to do augmentation, we learn this time not a GAN, but rather a VAE. And this variational autoencoder jointly learns the embedding with the graph at the same time. So we do message passing as well as representation learning together, and we are iterating. And what's nice about this, it gives us a way to really learn the relationships between the graph, and then we can permute on the basis of these graphs the other relationships, thereby being able to augment the data set. Is this working? I'm going to be honest, just somewhat. So it only works in some cases. So tabular data augmentation, still I would say very much a frontier that's up for grabs. And again, one idea is, can we use multimodal data, imaging and tabular data, to augment tabular data? This would be quite exciting, I think. Another one is, can we use other types of priors? Priors that may come from imaging to empower the tabular data rather than graphs. Or maybe other ideas. I hope we can develop some together. I also want to say a few words about a very crazy scenario envisioned by my student Nabil, who comes from South Africa, where not a lot of data sets exist. So he said, well, I'd like to build something for my country, and we don't have a lot of data sets there. So can we have in ultra-low data regimes a way to generate data? And what he started to look is whether large language models can generate data for a country like South Africa, where we don't have a lot of data. And the idea there was to build something that we call curated large language models, where what we do is we are using knowledge about the data in South Africa to prompt a large language model, which we know may hallucinate and may create a lot of crazy data. And in order to prevent that from happening, we are going to use not only knowledge, but also data itself. So if we have just a few examples from South Africa, from just a few examples, we are using real data, curated real data from South Africa to further augment this generation process, thereby curating and adapting the responses of the large language models on the basis of real data. So curation through data. I find this quite exciting. I don't think, again, it's the end of the journey, but I find it quite exciting because we often are lost if we don't have enough data. So this is, I think, an important way of thinking about it. What about other scenarios? Can we do better? Can we do better in high-dimensional scenarios? Another thing you could do besides creating data from scratch using large language models would be to do adaptation from other domains. Can I take data from other countries where I do have more data and adapt it for South Africa, for instance? And this is a problem that I think it's much more well studied for many years in the machine learning community, which is the whole idea of transfer and domain adaptation. But what's interesting is not only transfer where I take data, let's say, from Germany and I try to transfer to the UK, or from Germany and I try to transfer to South Africa. That's one thing, but I think even more exciting is when there is not only population drift and shift, but also the covariates are different. So what happens if you have some measurements in Germany, but you have no such observation in South Africa, and vice versa? So you have not only distributional mismatch, but also feature mismatch. In that case, I still think a lot better can be done. Early work from our lab that tried to address this is called radial GAN, where we were using still GANs. Again, I think the world came quite far since then, but still I don't feel this problem is sufficiently addressed. And in particular, problems that I don't think are addressed is, can we determine which data you need, how much data, from which domain? So how to really do this transfer in the case we have distribution mismatch and feature mismatch? And can we do better data harmonization? 2 words about trusting synthetic data. We know that generative models are often creating data that's completely crazy. Here are some examples for DALL-E for imaging. But in the tabular setting, the examples are even crazier. So generation is beautiful, whether it's done with GAN, with large language models, or diffusion models, but it's often incorrect. So less glamorous is the problem of evaluating synthetic data. So while our papers on GANs or diffusion models tend to be immediately accepted, this work, which was much more important in my opinion, on evaluating synthetic data was rejected 4 times. So I just want to say that, such that the ones among you that work on this area are not discouraged. I find this work a lot more interesting and a lot more powerful, even though it was rejected 4 times before it was accepted. So the reason we were very much about evaluating synthetic data, we knew that a lot of our models, as well as our colleagues' models, generated a lot of crazy data, and the community tended to test in 2 ways, either using KL divergence or Wasserstein metrics, or using a metric which we ourselves proposed, which was train on synthetic, test on real. And this obfuscates a lot of problems. So we knew this, so we wanted to fix it. So what we did in a paper that appeared only in 2022, even though it was finished and it was on archive 2.5 years earlier, we built methods for evaluating synthetic data and looked at fidelity, coverage, and authenticity of data. So in particular, we looked at how representative the data is. So we looked at fidelity, at coverage, and generalization. And this is very important because, again, to paraphrase Lena's talk yesterday, if you test only on average, well, maybe many things you don't even know. And the data that you are creating completely eliminates the, let's say, black older population, and you don't even know it. So how do we do that? We built some different scores. So the inception score is very popular, but for many, for instance, tabular data, that's not very useful. So this augments and changes that. I won't talk much about it, but I wanted to say that this is important. And what we built, I think it's quite interesting because it allows you to audit the samples that you are creating. So it's very nice, you really can inspect your synthetic data. So if you are working with generation, I'd advocate taking a look at this paper to look at what you generate. So again, call to action, join us in this work on synthetic data. And join our SynCity project because we do not have enough people working on imaging. I want to say a few words about trustworthiness, partially because, again, Lena inspired me yesterday. So it's clear that we don't want just point estimates. We want to have uncertainty estimates associated with our predictions. And I think that this is indeed very important, as she says. And what we really want to have is true uncertainty quantification, such that we know what our models know and what they don't know. And this is very important if you want to do anything meaningful than just publish a paper. So I also want to have a rant about something that's very popular in machine learning, but I think is useless, which is this whole dropout idea. This sounds beautiful, and all of us do it, and it's very easy to do. So everybody says, oh, okay, let me put Monte Carlo dropout there. But this doesn't solve much. First, many of the credible intervals that you are creating with dropout are really wrong. Number two, this is not what we need, and for many reasons. First, this alters the quality of your model, and also credible intervals are not what we need in medicine. We want true coverage. So we want really frequentist guarantees. Again, I work myself on this type of dropout methods, and I've built quite a lot of them myself, but the more I use them, the more I realize that they are not the way to go. So in healthcare, the reason this is not enough is because we need methods to estimate for any machine learning model post hoc how accurate, so how confident we are in our prediction. So this needs to be done post hoc and not as part of a dropout method. We need to have generality such that I can put it on top of any machine learning model, and we need frequentist coverage guarantees. So what do I advocate? You may not be surprised. I think conformal prediction is easy and powerful. So conformal prediction, I think, is the way to go, and this does provide us true coverage. And this is model agnostic and distribution-free assumptions, so it's really quite powerful. And over the past years, we changed our religion from a Bayesian approach to a frequentist, conformal prediction type of religion. And we did a lot of work in this area, inspired by the work of conformal prediction. So we looked at treatment effects. We were the first to do conformal predictions for time series. We even built an automated framework for conformal prediction, because there are many different types of ways of doing conformal prediction. So being able to come up with the tightest, most robust methods. And again, this is important to have not only accurate coverage, but also accurate discrimination. And this is another key challenge. So coverage is one thing, but you want to have both coverage and discrimination. And the challenge is that at times conformal prediction doesn't work so well. So you may have constant width intervals, and that's not good enough. You really want to have really very good discrimination, and you want to be adaptive to the different types of information depending on how much information you have. So conformal residual fitting was a method that was proposed but doesn't work very well. So I want to propose to you another way of thinking that I think it's widely applicable, and I think it's widely applicable in imaging, and I know many of you are imaging people here. And this is using self-supervised learning, not to improve your representations. Everybody knows by now that self-supervision is a very good idea for prediction, but I propose to you to do one more thing. Not only to do self-supervision for improved prediction and representation learning, but rather self-supervision to improve your uncertainty quantification. Again, great work by Nabil and another fantastic PhD student from my lab, Alan. So what we did in this AI stats paper last year, we used self-supervised learning, so we used both labeled but also unlabeled data, and the unlabeled data can be useful to improve your coverage and accuracy, thereby building more trustworthy confidence estimates and having better discrimination. So that's something we did for tabular data, because that's what we do, but I think this would work well in imaging as well, and I hope some of you will look at this and try it for other modalities. So again, this allows you to have this adaptive conformal prediction that's even better calibrated. I talk too much, as always, so I'm probably going to stop. And unfortunately, this is an example that we did it for time series forecasting, so I know some of you may have videos. So if you have videos, please take a look at this. We did it for time series tabular, but I think it can be very nicely used for if you have CT scans or MRIs or any moving images, ultrasound. I think doing conformal prediction for video should be equally possible. So please take a look on the conformal prediction for time series and see if it's useful for you for moving pictures. I will not talk about LLMs because I don't have much time, but let me just show you this slide. I'm very excited about LLMs, and many people are asking me, what is the role of academia now that we don't have resources to train large language models? We don't have even resources to fine-tune them. Maybe you have them in Germany, I don't have them in Cambridge. And yet, I'm very excited about this topic because I think we as academia can do a lot. And we can do more interesting things than just fine-tuning, which in my opinion is quite boring, or for that matter, training yet another foundational model. What can we do? We can use cutting-edge AI to improve large language models, and conversely, we can use large language models to improve cutting-edge AI. How? I'll just give two ideas in words because I don't want to show to you slides since I don't have more time. One is, for instance, to use large language models to either enable you to improve optimization, which is ubiquitous in machine learning. We have at iClear a paper where we use it for a type of optimization that's very dear to our heart, which is Bayesian optimization. We do a lot of work on Bayesian optimization because that's very useful for model selection and automated machine learning. And what we are able to show is that large language model can significantly improve Bayesian optimization. But my belief is that it can improve other types of optimization methods. So LLM improving cutting-edge AI. How can cutting-edge AI improve LLMs? One of the most important things we do right now, and all of us are doing it when we are using large language models, is prompting. So when we prompt, we know that there is not one best prompt. And people do a lot of ideas on better and better prompting. And what we show is that by using ideas from inverse reinforcement learning, you can design personalized prompts that are good for the task at hand. So again, using an idea from cutting-edge AI to improve how we deal with large language models, whether it's in medicine or for fun. So something a little bit different. And we hear a lot about alignment, where we are doing reinforcement learning type learning from feedback, so RLHF. So we try to align large language models with human preferences. What we advocate is to do something in addition, which we call inverse alignment. Can we learn how to prompt to better align this time the human preferences to what the large language models know to be able to better prompt them? If you are interested, we have a paper that tries to do that, and that's another iClear paper called Prompt IRL. So why did I tell you this? I wanted to make you enthusiastic if you are working in academia, not to do yet another foundational model, but rather to use your immense creativity, which you are learning in the academia, to really use large language models to empower your machine learning models, or conversely, to use machine learning models to empower the beautiful world of large language models, way beyond just another fine-tuning. So let's get as academia, let's show the industry that we can do equally interesting things, and maybe even more creative, and hopefully more human empowering things. With that in mind, I'm done. And I just want to say two things. One of them is that we are running together with my students an inspiration exchange, which is online. Some of you I know are joining it, but I'd like to have more people from your community joining us. So please just subscribe and join us. We have talked quite a lot in the last two sessions about large language models. So if you want to see what we are working on large language models, please take a look at the YouTube videos from the last two sessions. The next one will be about totally new frontiers on interpretability. And we are going to show to you a totally new way of thinking introduced by a new student, not a new student, a very brilliant student from my lab, Christophe, how he thinks about interpretability and why he believes post hoc interpretability, whether it's Lime, Schaar, or other things that we have done, is not the way to go, and how to think differently about interpretability. So join us in this debate. And finally, we have a summer school, which we are running in the first week of September. And we are going to talk about large language models, data-centric AI, and especially how large language models and machine learning can cooperate again for human empowerment. So this is online, so please join us if you are interested. Thank you. And sorry to talk so long.
Yeah, thank you very much, Mihaela, for this fantastic talk. I'm so impressed because yesterday you gave a really inspiring talk and basically the topics are disjunct. I don't know how you do it.
But this was motivated by your talk. So okay. This is a talk trying to say, I agree with what you are saying, and I'm so enthusiastic about what you are saying. And since my lab is working primarily on tabular data, it would be fantastic to join forces with your vision to do multimodal, because I think that everything I said, it's at another level if done multimodally.
Yeah, thank you so much. I think this goes to the whole team. Okay, so Mihaela's ready for questions. I take one from Moritz Gerstung, who's actually one of the genomics AI PIC at DKFZ. And it's about shortcut learning. So he says in medical data, there's often comparatively little signal, much irrelevant background. Also, data often come from a limited number of sources, each with distinct characteristics. What are, in your view, the best strategies to ensure that models don't learn the noises and biases and generalize them to unseen domains?
So first, so the question is complex, and I'm not sure how to understand it, because there are two ways to think about it. One is, when we talk about models, do we talk about predictive models, or do we talk about generative models? And let me say a few words about both, just very briefly. So if it is, we have predictive models that we try to make them more generalizable. What I would advocate is to create synthetic data that contains different amounts of noises, different amounts of hardness, to really stress test these models. I'm really quite excited about this way of thinking. So data shifts, drifts, augmentation, noising as a way to test predictive models. If on the other hand, the question is about how do we test our generative models, that they are indeed generalizable and accurate, that's when I talked about this painful paper which got rejected 50 times before it got accepted. That's what we try to do with that type of paper, and we are just looking at representativeness. We didn't look there at noise or errors. We just look at, is this data resembling the real data in terms of, again, coverage, generalizability. More recently, again, my student Nabil Sidat said, you guys in synthetic data, you always clean the data before you generate synthetic data. I said, this is crazy, because you create this very beautiful synthetic data, and then you give it to researchers to build predictive models. What good is that? Because then you'll build these models which will fail in the real world because they've built on sanitized data. So what he did very recently, again in Datasets and Benchmark Tracks NeoRIPS paper, he put the data-centric lens and the synthetic data together, and what he's looking at is, do we generate synthetic data that's not only high fidelity, but also contains all the messiness, all the errors, all the missingness, all the hard examples in the real data. So it's a pretty crazy idea. Can we generate synthetic data that contains all the messiness of real data, and can we validate not only representativeness of the coverage, but also representativeness of the mess in the data? And I think this is interesting. None of this work is final, it's just beginning of an agenda and our excitement about data issues. But I'm not sure that question...
I believe that he was more talking about the predictive aspect, not the generative aspect. And I mean, for example, in our data, we have the problem, I mean, we're trying very hard to generate synthetic data. We started this actually in 2013, and we're still not there to have, you know, the full realism of real life. And we observe that, for example, if we try to remove shortcut learning by disentanglement or something like this, I mean, we do get nicely structured latent spaces, but in the downstream task, we don't really get an improvement. Maybe he was talking along these lines. And then, of course, there's also the second issue that you don't...
Could I say a few words then about that? So definitely generating high-dimensional data is hard. I want to propose something against disentanglement. So everybody talks about disentanglement and loves disentanglement, and there have been billions of papers on disentanglement, but I really don't understand still what, and I've written some. But I started to no longer believe in this disentanglement, because at times we disentangle some useless stuff. So I want to propose to you not a way of solving it, but a way of debugging it. So together with a student called Jonathan Krabbe, we started to look at unsupervised interpretability. So can we look at an embedding space that's created through a disentanglement process? And can we understand really what has happened? So we hear a lot about interpretability of predictive models, which features were important. But here is interpretability in the representation space. Can we make these representations more interpretable to humans such that they can understand whether the disentanglement is what we really want, and much more guide our representation learning in an interpretable way? So Jonathan Krabbe, and I don't remember very well how the paper is called, but it's about unsupervised interpretability. And we show that a lot of this disentanglement is actually doing, you believe, and we take representative examples from the literature and show that it does totally the opposite thing.
Yeah, that's our experience, basically. We didn't really make them work for our problems, at least.
So maybe if you have a way to understand it, maybe you can fix it. It would be amazing if you could use these tools as diagnosis and then you would do something better. So again, maybe collaboration.
Questions to Mihaela? Marco, and then you have a microphone, and then Stefan.
Yeah, first of all, thank you so much for your talk. You touched also on evaluating data quality, and I was wondering whether evaluation gets increasingly or exponentially harder with higher dimensionality. So would you say there is some sort of curse of dimensionality for data evaluation as well?
Very cool. Very cool, yes. Short answer, yes. And I think it's understudied and important. Well, because as you are having this complex manifold that you need to represent correctly, you need to make sure that indeed all these relationships in this manifold are correctly represented and all the structure is correctly represented, because it could be signal that's informative. So the answer is yes. The question is how to do it correctly. And there is one way of thinking, but I'm kind of sick and tired of that way, which is let's learn a graph and let's make sure that this graph still stays correct in the synthetic data. Fine, you could do that, but I hope we could do something better, because these graphs are not always everything there is. So I think the answer is yes. The question is how, but I find it very exciting.
Stefan? Doreen?
Yeah, thank you so much for the great talk. My question is going in a similar direction and also very much in the direction of Nabil's work. So Nabil proposes many works which look at the data themselves, and also this synthesizing of data might have the problem that even if you validate it with the real data, you still might have some shortcuts in there, right? So I was wondering if you, and I know you're working very closely with physicians, do you also have them maybe have a look at this data to actually prove or show that this is actually useful, what you're learning there in your synthetic data sets?
This is a very good question, so thank you for it. So first, like I said, and maybe I said it too fast or not good enough, I'd like to increasingly validate not only on real data. Validation on real data is needed, but I'd like to go beyond, because as we said, this work, for instance, from Google was validated based on real data and still failed in the real world. Because again, at test time, you may have very different types of data. So what we are trying to do increasingly is to ask, to prompt either a large language model or ideally prompt an expert about the domain where this method will be used, and then try to instill those things in the synthetic data to to evaluate in this way. So the way we did it in free-as testing was by asking, for instance, clinicians, how do you see these subgroups changing in your problem of interest? How do you see the number of anomalies changing? So right now we prompt an expert and then we generate on the basis of this prompting of an expert all this variation. Again, a begin, but this is, yeah, I agree with you. It's just not enough.
Okay, one question from the online audience, then you. So how to deal with hallucinations in synthetic data?
Very, very good. So that's to some extent, I'd advise you to look again at my superstar student, Nabil. He is doing this, I'm very excited about my students, and some students are, it's difficult to keep up. Nabil is one such student. And the reason I'm so excited about him is he's very reality-centric, so he really worked in industry before joining me, so he really understands the real world, and non-stop he turns a real problem into something interesting to work on. So in this work that, again, it's a begin, but I hope it can inspire you, it's called curated large language models, so it's called curated LLM. What we are trying to do is to hold out data and knowledge to compensate for these hallucinations, to curate the large language, not to fine-tune, but rather to curate the large language model and make sure that these hallucinations do not appear. So curated LLM, take a look for some steps along the way. So, and it's exactly targeting these hallucinations of the large language model.
Thank you very much for your talk. My question is about the cleaning of the data, since you mentioned for
Cleaning.
the synthetic data that you could argue that you don't even need to clean it. Since I come from classical machine learning as well, this is a bit surprising for me that data cleaning is very important for a lot of the tasks. So
I agree with you. No. I said something else, and now I realize I maybe confused people. So no. Data cleaning, data curation is definitely very important, and this is how I started. So that piece, it's very, very important. Please look at DC-check, for instance, and definitely. The statement I tried to make is a little bit different. What I said is, imagine you take real data, you clean it, you generate synthetic data, you give it to the machine learner builds that methods, the methods are built, and then this method is given to a practitioner. This method will be then applied on real-world messy data. And if that person doesn't do the data cleaning necessary, the methods will fail. So what we are saying is not that data cleaning is not super important. What we are saying is that if we generate synthetic data with the role of doing realistic data, we shouldn't look, like I looked in the past, just at coverage, how representative it is, how fair it is. You should also look at all these errors and messiness and missingness to create truly realistic synthetic data, also with respect to these impurities in mind. Because then when you give it to the researcher will need to do the data cleaning and to do the data curation. Otherwise, we are back in non-reality-centric AI, where most of the ML community is. They truly believe, and much of my lab still believes, that we will get a super clean data set, and they demand a super clean data set to be given to them. They don't want to dirty their hands with anything real, because the reality is the machine learning community doesn't reward that very much, and everybody has a super clean data set. Then we will get 50 million citations, but we will not do anything that's useful for the world. So the rant is against that. I'm preaching to the choir, I know.
A quick follow-up, would you then say it's also important to do the cleanup then afterwards, not only to export sort of the synthetic data, but also to have a sort of common data cleaning pipeline for the real-life applications?
Definitely. This is exactly what we have written about in DC-check. Please take a look at this paper of Nabil called DC-check, where we exactly, it's not a method, it's actually a call to action from the entire world to build these pipelines, and we propose a very clear way of reporting, your data cleaning, such that we have a standardized way and we work towards standardization. And we build methods together. So DC check is, if you like, a way of thinking about these data curation issues at all different stages. And also even a form that we hope that the researchers will use to report the data cleaning. Because if we want to learn from each other and also to be able to do reproducible research, we need to say what we have done to the data. Because we may have done good and bad things to the data, or maybe you do something to the data and do something very different. This is, by the way, non-stop in Mimic. People clean Mimic, and they do different things in it, and they obtain very different results, and then they compare against it and declare losers and winners without even knowing whether the comparison has been fair.
Thank you very
Okay,
much.
one concluding question. So let's say I gave you, or somebody gave you, 20 of the best AI people in the world. You can also complement with clinicians and unlimited compute and expense money. And now you can work on one big challenge with them. What problem would you tackle?
Wow, that's a tricky question. I'll give two answers to it, but they're nested. I would work on reality-centric problems. So what do I mean by that? No matter what excites you, in my case, medicine and education excite me, even though I worked in others in the area. I really want to look at the real world, what problems we have today, and try to solve them. I'm an engineer rather than a scientist by training. So I'm less interested in science questions, not because that they are not important, but this is not my strength and what inspires me. What inspires me is real world problems. And what are they? Anything from fixing healthcare systems and building large-scale pipelines to paraphrase one of my clinical collaborators. If we want to save a lot of lives, we don't need to cure cancer. What we need to cure is our wrong, and I'm not talking about Germany where things may be better, but our wrong healthcare systems. The healthcare systems are in US and UK so broken, if we fix that, we will save even more lives than if we cure cancer. And why people find that interesting, I find this interesting, this is very much a systems problem, a messy problem, a large-scale problem. It's exciting to me. So reality-centric first. And secondly, I'm very concerned, I'm very excited about large language model, I'm very excited about machine learning and AI, but I'm also concerned about humanity. So the second one that fits in reality-centric is human empowering AI. AI that is really making humans smarter, more in control, more capable, and not marginalizing. Because what I'm very worried about is humans will have more time, more free time, and like in WALL-E, the movie, they are going to just watch stupid social media online and do nothing else. So I would like to build AI that's human empowering, makes us smarter, more capable, to able to absorb more information and creating bigger brains.
Okay, thank you so much. Let's thank Mihaela again for the great talk.